We now turn our attention to acyl transfer reactions in which the nucleophile is a molecule containing oxygen, and the oxygen atom is the nucleophilic atom. And we're going to look at two very important examples of such acyl transfer reactions, namely transesterification and hydrolysis. So transesterification, as the name implies, is the conversion of one ester into another. So in the example given on the screen, we have a methyl ester being converted into an ethyl ester. Note it is the group to the right of the oxygen atom that is changing. The group to the left of the carbonyl group remains the same. Hydrolysis is a term you have seen before, and that is breaking something apart with water, hydrolysis. And what that means in this case is that we are converting a carboxylic acid derivative into a carboxylic acid or its conjugate base, namely the carboxylate anion, by reaction with water, at least as one of the reagents. And the reaction will give either the carboxylic acid or the carboxylate anion, depending on what conditions the reaction is carried out under. Under acidic conditions, you are going to get the carboxylic acid. Under basic conditions, you are going to get the carboxylate anion, because carboxylic acids would be deprotonated under basic conditions. Okay, so in the last video, we looked at a mechanism in which we were using an amine as a nucleophile to convert an anhydride into an amide. And for that particular reaction, the first step, the nucleophilic addition to the carbonyl group, took place under neutral conditions. And that was possible in that case because the nitrogen atom is a good enough nucleophile as a neutral nitrogen to be able to undergo that addition. When we move from the world of nitrogen to the world of oxygen, that is no longer the case. So just like with simple carbonyl addition, the reaction of carboxylic acid derivatives with oxygen nucleophiles will not take place under neutral conditions. Okay, because once again, we've seen this before. Attack of a neutral nucleophile on a neutral carbonyl group will produce an intermediate with both a plus and a minus charge. If the nucleophile is oxygen, that will lead to a plus charge on one oxygen and a negative charge on another oxygen in close proximity in the same intermediate. And furthermore, the positively charged oxygen is a strong acid, and the negatively charged oxygen is a strong base. We are not going to take two neutral compounds and generate an intermediate with a strong acid and a strong base in close proximity. In short, the activation energy for this process is just too large. Okay, so just like in the case of simple carbonyl addition, when we talked about acetals and hemiacetals, these reactions need to take place under either acidic conditions or basic conditions. So under acidic conditions, the first step is going to be protonation of the carbonyl oxygen using acid to make it a better electrophile. Okay, so now the electrophile carries a positive charge, and because it is positively charged, it is now much less stable, so it is higher in energy. Here's an energy diagram showing that the activation energy leading from the positively charged ester to the intermediate, the tetrahedral intermediate, is much lower because the positively charged ester starts at a higher energy level. And then I also want you to note that all intermediates in mechanisms that are taking place under acidic conditions are going to contain a positive charge. Okay, there are not going to be any negative charges under acidic conditions. In contrast, this reaction can also take place under basic conditions. So my definition of basic conditions is that the oxygen nucleophile is anionic rather than neutral. The anionic oxygen nucleophile was generated at some point in the past from a neutral compound using base before putting it into the reaction flask. But we know that that is possible. You can buy a bottle of sodium hydroxide, which is of course the conjugate base of water. You can buy sodium methoxide, sodium ethoxide. The protonated carbonyl that you need under acidic conditions you cannot buy. You must generate that in the first step of your reaction. But under basic conditions, we can already buy the nucleophile activated by deprotonation. Okay, so in this case, you can see an example on the screen of the anionic nucleophile attacking the carbonyl carbon, breaking the pi bond, putting the electrons onto the oxygen to give you a tetrahedral intermediate that has a minus charge instead of a tetrahedral intermediate that has a positive charge. And then in terms of putting this onto an energy diagram, the hydroxide is intrinsically less stable than water is. It's a base, it wants to react with something. It could be a nucleophile also, as we see in this reaction. So it is higher in energy, and that also reduces the activation energy for the nucleophilic attack step. Okay, so the other thing that I want to talk about before we get into the very specific mechanisms is the topic of proton transfers. Specifically, when do we use them? So depending on the reaction conditions, there can be up to 3 proton transfers in the mechanism. So the main steps in an acyl transfer mechanism is you have addition, nucleophilic attack, followed by elimination, loss of a leaving group. But if you're doing the reaction under acidic conditions, you have to add 3 proton transfers to the mechanism, which ends up making the mechanism longer. Whereas under basic conditions, if we assume that we are starting with the nucleophile already deprotonated, there are actually no proton transfers. So the specific functions of these 3 proton transfers are as follows. The first one is needed to protonate the carbonyl compound to make it a better electrophile, as we saw 2 slides ago. The second one is to produce a good leaving group that will be able to leave as a neutral molecule in the loss of the leaving group. And then the third one is to deprotonate a positively charged final intermediate in order to give a neutral organic product. Okay, again, these extra proton transfers are necessary under the acidic mechanism, not under the basic mechanism. So what we're going to do in the next 4 videos is go through first transesterification and then hydrolysis. We will do transesterification under basic conditions first, because that's the shorter mechanism. Then we will look at it under acidic conditions, and we will do the same thing for hydrolysis. Basic conditions first, followed by acidic conditions.